Good morning, Academy students. We are officially starting Unit 2 today, which is Bonding, Nomenclature, and Introduction to Chemical Calculations. For this week, we're just looking at nomenclature, and specifically, we are looking at ionic compounds. An ionic compound contains a metal and a nonmetal. When we get back from the break, we'll be looking at our covalent and our acid compounds. So I'm going to start by actually looking at a few examples of ionic compound formulas and chemical names. And I want y'all to note some of the patterns that we see occur when we have a metal bonding with a nonmetal. So remember that my ions for our representative elements, for elements in groups 1, 2, and 13 through 18, we can know the charge of those particular elements just based on their position on the periodic table. So the fact that indium is in group 13, we know that it always forms a +3. And the fact that selenium is in group 16, it always forms a -2. Now, when we take those ions and we get that chemical formula, notice what happens to those charges. Same thing with my barium and my bromine. When we go from the ion form to the chemical formula, note what happens to the charges. Now, with 4, 5, and 6, we have multiple letters. We've got 3 or more capital letters, and those things are using what we call a polyatomic. We're actually officially going to start using page 2 of our cheat sheet, where we have our list of polyatomic ions. So notice when the charges cancel out, when they're the same, we don't write the numbers. We don't write those exponents. But if they're different, we swap and drop. A couple other things to notice is the names. All of the ones that have only 2 capital letters all end in the same thing. All of the ones that have 3 or more capital letters end in TE, and the ones that have only 2 capital letters end in IDE. Those are patterns that we can see in our nomenclature rules. Now, I mentioned polyatomic ions. This is our an example of our cheat sheet that actually has all the polyatomics that we will use in this course. Notice that it gives you the formula with its charge and its chemical name. I don't expect you guys to memorize polyatomics, so it will make your life a little bit easier if you do learn some of them, but you'll always have this particular cheat sheet. So it tells you their names, and anytime you see 3 or more capital letters, you just have to get used to looking at the second part of your cheat sheet. Now, a couple of things that I did not notice didn't note with the opener was that on all of them, the metals are written first. And that's one of the first and foremost rules. The most metallic element is always written first. Also, the metals didn't change their name. So the metals always keep whatever their name is, and the non-metals are the ones that actually change their ending. So if it ended in 2 capital letters, it ended in IDE. If it's 3 capital letters, we had to look at our cheat sheet, we had to look at our polyatomic ion, and it ended in a TE, either ATE or ITE. There are a few exceptions with polyatomics that don't end in ATE or ITE, but those are few and far between, and they're on your cheat sheet. So we kind of have 2 choices with our charges. They either balance out, they cancel out, and we don't write them, or we swap and drop. So also referred to as crisscross. We take whatever was at the top and we swap it to the other one and drop it to the bottom. So we end up with Na2O1. Now let's look back at what we already remember from Unit 1. We already know that the proton determines the identity and that my proton is equal to my atomic number. If we change the number of protons, we've changed the atomic number, we've changed the element. My valence electrons are the electrons that determine the chemical properties. That's the thing that is constant within a particular group. That's why all the elements in a group have the same chemical properties. Now remember, for my groups 1, 2, and 13 through 18, the valence electron actually equals that last number of the group number. Now my valence electrons are the ones that are in that outer energy levels. I already said that. And our elements gain or lose electrons to achieve that octet. If we only have 1 or 2 valence, they lose them to form a positive charge, which we call a cation. And if they have 4 or more, they tend to gain more electrons, which gives them a negative charge, which we call our anions. Now, my nonmetals always gain electrons, and my metals always lose electrons. Notice that we're not talking about metalloids because they can actually do either or depending on the situation. So the other thing that we already know is the valence electrons for each of the groups. Like I said a moment ago, it is related to the last number of the group number. So if I've only got one number in the group number, it's easy peasy. But for 13 through 14, you've got to ignore that first number and focus only on the ones digit. This tells me the number of electrons that are in that outer energy level. And if we only have a couple, we're going to lose them to form positive charges. Group 14 is the group that can go either way because it is halfway from one end to the other. With group 15, I now have 5 valence electrons, and it is easier for it to go out and steal 3 electrons. So we kind of start counting down, till we get to our group 18, which is our noble gases, and they don't form ions. They don't typically form bonds. So this particular pattern, this charge, or my ion, or my oxidation state, whatever you want to call that number, you want to memorize. This is the ion that every element in those groups form every single time. With my group 14, my metal tends to form my positive charges, and my non-metal tends to form the negative charges. Like I said a minute ago, we're going to start with ionic nomenclature. And ionic nomenclature is a metal bonded with a nonmetal. And the thing about elements is that they gain or lose electrons to achieve that octet. Well, with an ionic compound, they formed those ions, that positive charge and that negative charge. And those ions are attracted to each other. Now, my metals will lose their electrons and drop down an energy level. My nonmetals will gain electrons and fill up that outer energy level. Either way, they end up with that octet, and we have a positive ion and our negative ion, and they are strongly attracted to each other. Ionic compounds are the strongest compounds that are out there. Now, ionic compounds are neutral, so the positives have to balance out the negatives. This is what makes ionic formula writing so very, very predictable, because all compounds are neutral. They don't have a charge overall. My positives have to balance out my negatives. So the easiest way to do it is to look at the charges and ask yourself, well, do they equal 0? If they don't, like my 2 and my 3, I add them up, they don't equal 0. And they're not both divisible by a 2, 3, or 4, then we just swap and drop. We take what is the exponent for the aluminum, and we give it as a subscript for the oxygen. We take what is the exponent for the oxygen, and we give it as a subscript for the aluminum. This is the easiest method to write your chemical formulas. So I ask myself, do these charges add up to 0? No, they don't. Are they divisible by 2 or 3 or 4? Yes, they're both divisible by 2. So I'm going to divide them both by 2. And then I swap and drop. I end up with a 1 beside the PB and a 2 beside the O. All right. Even if it's a polyatomic, it doesn't get any more difficult. One thing I do encourage students to do is put parentheses around the polyatomic because it makes your life a lot easier. But look at the exponents. Ask yourself, do they equal 0? Well, they don't add up to be neutral initially. They're not both divisible by 2 or 3 or 4. So we swap and drop. I still write that chemical formulas the way that they was. So that polyatomic stays as a polyatomic. We end up with the 2 outside and the 3 beside the MgPO4. By swapping and dropping, we are balancing the charges. We are showing that for my aluminum, in order to equal 0 and balance out the -2 of the oxygen, so I add up all my charges and I can see that, yes, now they equal 0. Well, in order to balance out and equal 0, I had to have 2 aluminums and 3 oxygens. Now, swap and drop isn't the only method. It is the easiest and the quickest, but you do have to remember to check to see if your charges can reduce. So Pb4O minus 2. They got to equal 0. Well, I can add another oxygen. Now they equal 0. I've got a +4, -4. This is how come we ended up with a chemical formula of Pb1O2. It takes 1 lead to balance out 2 oxygens. Now, here's the thing about chemists. We tend to be lazy. So we typically do not write 1s. If you want to write the 1, you can, but you don't necessarily have to. So also note that the most metallic element has to go first. So if I'm looking at oxygen and sodium, I can see that sodium is in group 1. It's a metal, so it's got to go first. Anything in group 1 forms a +1 charge. Oxygen in group 16 forms a -2 charge. Ask myself, did these equal 0? They don't. So I swap and drop. I end up with a 2 besides my Na and a 1 beside my O. Or, if I'm a lazy chemist, NaO. Looking at the next one, I've got nitrogen and aluminum. Of these two, aluminum is my metal. It's the one that's to the left of the stair, so it has to go first. It's in group 13, so it's a +3. Nitrogen in group 15 is a -3. Do these equal 0? Yes, they do. So if they already equal 0, it only takes 1 of each element to balance it out. So therefore, my chemical formula would be AlN. All right, calcium and carbon. Well, calcium's in group 2, it's a +2. Carbon's in group 14, but it's the non-metal, so it's going to form a -4. These don't add up to 0, but they are both reducible. They're both divisible by 2. So we reduce and then swap and drop. So my chemical formula ends up being Ca2C. I can get this the other method by just looking at the charges and adding more of each element until they balance out, but it will take a little bit longer. So I've got to add more calciums. I now have a total of a 0 charge. So I see that I have 2 calciums, 1 carbon. Polyatomics are no different. My metal still's got to go first. If it happens to be a positive polyatomic, it goes first. Ba is in group 2. It's a +2. PO4 -3. That whole thing has a -3 charge. They don't add up to equal 0. They're not both divisible by a 2, 3, or 4. So we swap. 3 ends up beside the barium. Keep the polyatomic like it is. 2 ends up beside the phosphate, PO4. So that's writing the chemical formulas. Now, once you have the chemical formula, you're going to need to write the name. Depending on how many capital letters you have, the name is going to vary from element to element, or compound to compound, sorry. If we have 3 or more capital letters part of the name comes from the polyatomic ion sheet. And we look at it and we see what that special polyatomic ion's name is. If there's only 2 capital letters, then we change the ending of the non-metal. Now, this applies to elements in groups 1, 2, 13 through 18. In addition, it applies to metals in groups 1, 2, and 13, in addition to zinc, cadmium, and silver. Those are 3 transition metals that only have a set charge. Zinc and cadmium always have a 2, silver always has a 1. So when you're writing their name, the first thing you got to do is write the name of the metal. So I'm going to pick on my calcium and my oxygen that I had a minute ago, and my barium and my PO4 I had a minute ago. So the anion, my negative ion, if it is a polyatomic, I write whatever its special name is. 3 or more capital letters tells me it is a polyatomic. So I look on my little cheat sheet and I see that my polyatomic's special name is, oops, too far. PO4 is phosphate. Your polyatomic, with the exception of NH4, are always at the end of the compound. So PO4 has a special name. Its name is phosphate. Ba is a metal. It doesn't change its name, so therefore it is just barium. So Ca and O, only 2 capital letters. That means I write the name of the metal, calcium. My O is a single non-metal, so we change the ending of oxygen to IDE. General rule of thumb is you keep the first syllable. So oxygen, we keep the ox, and we place the rest with IDE. There are a few exceptions, but Ms. Raines does not count off for little spelling errors. So this thing is called calcium oxide. The other compound is called barium phosphate. So what is Ca3N2's name? Well, I see 2 capital letters. It begins with a metal, so I write the metal's name, calcium. N, that's a nonmetal, not a polyatomic. So nitrogen, I keep the first syllable, and I replace that ending with IDE. So we end up with calcium nitride. Ca3PO4. Oh, for some reason I like picking on PO4. So PO4 we already know is phosphate. Ca we already know is calcium. Put them together and you get calcium phosphate. So 2 capital letters. This is an L, not an I, because if it was an I, it'd have a dot. I've got K, which is potassium, C, chlorine. We keep the chlor, keep the first syllable, and replace ene with IDE, potassium chloride. Al, aluminum. We've already seen where chlorine becomes chloride. Ca is calcium. C is carbon. So carbon, replace that last syllable with IDE. Pardon me, calcium carbide. Number 4, INN. 2 capital letters tells me that I'm looking at just elements. In is indium. Nitrogen, we keep the nite and replace the ogen with ide, so nitride. So the next 4, notice, have 3 or more capital letters. That means I have to look at my polyatomic ion sheet. So I cheated and I took it and I stuck it on the screen. Either way, RB is rubidium. PO3, my cheat sheet tells me, is phosphite. So that thing all together is called rubidium phosphite. ALOH, I see 3 capital letters. Al is a metal, so aluminum. OH, that polyatomic, keeps its name, so aluminum hydroxide. Remember, I said most polyatomics in a TE. This is one of the few exceptions. 3 capital letters, IN, indium. SO3, I find my SO3, and I can see that it is sulfite. Put the 2 pieces together, and you get indium sulfite. Last but not least, number 8. Notice I don't have a metal here, but I see some parentheses at the beginning. This is the one positive polyatomic that forms a compound that we will see. It's acting like the metal, therefore it is written first. It's a polyatomic. It keeps its special name. So bromine, we keep the bro and replace that ending with IDE, bromide. So the whole thing is called ammonium bromide. So ionic compounds, writing your formulas, either reduce the charges and then swap and drop, or just write the letters if they already equal 0. With your names, they're either going to be one of the polyatomics, or it's going to end in IDE for that non-metal, and the metal always keeps its name.